AP Calculus BC, Unit 8, Day 9, Office Hours. This is a review assignment. It's got some good problems. These first ones just say express in closed form the lower limit of n equals 1. Which might be a little different than what we're used to. A lot of times we do n equals 0, but either way. Now, these aren't guaranteed to be geometric series. If you multiply the bottom by 5, that works. Multiply the top by 2, that doesn't work. So, sometimes it helps to write like some really notes: 5 squared, 5 cubed, 5 fourth, 5 to the fifth. But then this looks like 2 times 1, 2 times 2, 2 times 3, 2 times 4. So if we were to write n equals 1, now notice the alternating signs. That's an easy thing to put, but easy to miss. So it looks like, and by the way, this one is not geometric. It has a little bit of geometric to it and some other stuff. So if we write this, we'd start at n equals 1 to infinity. We definitely need a negative 1 to the n plus or minus, or actually to the n. That's good because it starts with a negative. The top looks like just 2 times n, 2n. The bottom looks like it's 5 to the n plus 1. So there you go. Next one, again, doesn't look geometric. Looks like we're adding 2 to the top each time, right? On the bottom, it looks like we're adding 3. There is this alternating sign thing. That's easy to fix on its own. So if we start at n equals 1, n equals 2, n equals 3, n equals 4, we're adding multiples of 2. So we added 2 times 1, we added 2 times 2 to the first one, 2 times 3 to the first one, I think. Yeah. We added 2 to this, and then we added 4 to this, and then we added 6 to this. Okay, so I think that might help. And here we're adding multiples of 3, so we added 3, and then 6, and then 9. So let's see if we can write this. N equals 1 to infinity. The negative 1 to the n power, that's easy. The top, we're starting at 7, and like I said, we're adding multiples of 2 to it. So I think it'd be 2 times n minus 1, because we don't want to add 2 at the beginning. Actually, yeah, I'll write this a different way. I just thought of something, but I'll go ahead and finish doing it like this. On the bottom, it's 2 plus 3 times n minus 1. Now, we could either just simplify this, or we could have taken the approach that, the first one's actually 5 plus 2 times 1. We could just start at 5 and we wouldn't need the n minus 1. Same thing on the bottom. But if we distribute this, it has the same effect. So you have a 2 minus 2 if you distribute this. So it's 5 plus 2n. On the bottom, you have a 2 minus 3. So that's 3n minus 1 if you want to lead it with positive. But either of these works. Okay. All right. Next one, if possible, find the value of the given series. So you're going to have several problems like this on your next test, 5 of them, where I give you either open or closed form of geometric series, and you don't have to rewrite it. You don't have to write open to closed to open. You can choose to write out the terms if you want, but I'm really just trying to find the value of the series. So that's the sum of the series. If possible, not possible be because it diverges. So then you would write diverges. So here, this is your A value, and it's kind of hard at first. Now remember, anytime you want to find the R, you can take a term and divide by the previous term, and that should give you the R if it's geometric. Let's check it. If you multiply this by negative 2/3, you get negative 4. If you multiply this by negative 2/3, you get positive 8/3. So that's good. That's our R value. You want to make sure, and I want to see work showing that you've done this, make sure it's less than 1, so it converges. So the sum equals a over 1 minus r. I like to just write that just to make it easier for me to remember it the next time. 1 minus negative 2/3. So it's going to be 6 over 5/3. So that's going to be 6 times 3/5. So that's going to be 18/5. Okay, that's the kind of work I want to see. Next one, next one's easier. This is your R value. Now, be careful. Some people are like, oh, this is A. Nope, that's not A, because we're starting at n equals 3. So the very first term, if we could plug in 3, would be 3 to the third, which is 27. So negative 27, negative 54 over 4 cubed would be 1664. We could reduce it, which might make the math a little easier later. To that, that's the first term. That's your A value. Your R value, you can double check, make sure it's negative 3/4. Is it less than 1? Yes, it converges. This is the work I need to see on problems like this to give you full credit. So we're good to use the formula. S equals A over 1 minus R. A equals negative 27 over 32. R is negative 3/4. So we get negative 27 over 32 over 7/4. So negative 27 over 32 times 4 over 7, which does allow us to simplify a little bit. So final answer is going to be negative 27 over 56. You can get negative sum. That's fine. So there you go. All right, next one. Next one's not so obvious, like, oh, because there's something in n plus 1. So usually what I do is I try and rewrite it to where everything is under an n power. So 2 to the n plus 1 is the same thing as 2 times 2 to the n, right? And then you have negative 5 to the n. So this is the same thing as 12 times negative 2/5 to the n. That's a little easier to. So this is your R. Absolute value of R is absolute value of negative 2/5 is less than 1. Yes, it converges. The A value, again, be careful because the first term starts at n equals 2. So that's going to be 4/25. So 48/25 positive. So then the sum equals A over 1 minus R. 48/25 over 1 minus negative 2/5. Be careful with the negative. Minus the negative, it becomes a positive. So 48 over 25. It's going to be 7/5. 48 over 25 times 5 over 7. So we're going to get 48 over 35. All right. Looks good. Okay. Next one. This is your first term for sure. Once we're in open form, that's pretty clear. Looks like we're multiplying by pi over e. Negative pi over e. Don't forget the negative. And I want to see that in your work. So is that less than 1? Well, pi is like 3.14, right? And e is like 2.71. So no, this diverges. And that's what I want to see as your answer. That's it. Do not use the formula. Okay? All right. Okay, these ones commonly use power series. So these are the ones that we've memorized. So can you write them down from memory? And if you can't write them down from memory, can you recreate them quickly? Because some of these I don't try and memorize. Like this one's easy because this is written in the form of S equals A over 1 minus R. So A is 1 and R is X, positive X. So you're just multiplying by X. Now it says, I don't know, probably in the test I'll make you write 4 or 5 terms. And then we could write the general term x to the a, which is the hardest part of writing the closed form because I want open and closed form. Okay, So if we start at n equals 0, n equals 1, then it looks like it's x to the n. So closed form is going to n equals 0 to infinity x to the n. We could also, I might also ask you to start n equals 1, and then that would be x to the n minus 1. Okay, the interval of convergence is -1 to 1. The way we find that is the absolute value of r, which is absolute value of x, has to be less than 1, and that's what you get, -1 to 1, interval of convergence. So now the next one, I don't memorize this one, but I know quickly where it comes from, and this is just a good skill anyways. It comes from integrating 1 over 1 plus x, right? And that series is easy to write. It starts with 1, and the r value is negative x, actually. So minus x plus x squared minus x cubed plus x to the fourth, dot, dot, dot. And you could even write the general term is -1 to the n, and then it's x to the, if we start at 0, equals 1, x to the n. Okay, so then we're going to integrate that, and that's what's going to give us these terms, because the antiderivative of 1 over 1 plus x is natural log of 1 plus x. So it's going to be x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus dot, dot, dot. Now we could actually integrate this. It should stop at -1 to the n, and then x to the n plus 1 over n plus 1. It's just power rule. So that's that. Now in closed form, n equals 0 to infinity, -1 to the n, x to the n plus 1 over n plus 1. Does it give you the same thing? Just double check. It also started at n equals 1 instead. Be -1 to the n plus 1 or minus 1, and then just x to the n over n. The interval of convergence is -1 to 1, which you get from this original thing right here. But if you might remember, this one's special, and you are allowed to use one of the endpoints. The one you can't use is the one that would give you natural log of 0, which is undefined. So the -1 can't be used. That one can be. Okay, so that's how I do that one. You could memorize the pattern if you want, but it doesn't come up that much, and it's a little more complicated. Now, inverse tangent, same thing. Inverse tangent is from the integral of 1 over 1 plus x squared. So, on a test, you'd only have to write this once. First term is 1 minus x squared, r equals negative x squared, plus x to the fourth, minus x to the sixth, plus x to the eighth, plus dot, 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 -1 to the n, x to the, if we go n equals 0, n equals 1, n equals 2, it's x to the 2n plus dot, 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 and we're going to integrate that. So these terms are going to be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9. The general term should still have a -1 to the n. Don't do anything to that. That's just a number. It's going to be the same value. It's the stuff with x, so it's going to be x to the 2n plus 1 divided by 2n plus 1, which is power rule. So that's what you use for your closed form. N equals 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1. No factorials or anything. Now, if we write that starting at n equals 1, it'd be -1 to the n plus 1 or minus 1. Make sure the first term turns out positive. And then be x to the 2n over 2n, right? That should give you the same thing. Now, interval of convergence is -1 to 1. But we can actually use both endpoints. Now, inverse tangent, yeah, so, okay. E to the x, I memorize this one. 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Now, the first term is actually x to 0 over 0 factorial, so it follows that pattern. The pattern is x to the n over n factorial. So pretty simple pattern. Closed form, n equals 0 to infinity, x to the n over n factorial. If we were to write it starting at n equals 1 instead, it'd be x to the n minus 1 over n minus 1 in parentheses factorial. This converges for all real numbers. Okay? Negative infinity to positive infinity is the interval of convergence for E and sine and cosine. Now sine, I just remember sine's an odd function. It has odd symmetry, right? Double symmetry across the x and the y. That's called odd symmetry. And generally odd polynomials also have that. So we're only going to take all the odd power terms here. X to the first over 1 factorial, and then it does change sign, x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial, dot, dot, dot. The pattern is we start at n equals 0, n equals 1, n equals 2. It has a negative 1 to the n, and then it has x to the double the n value, add 1, double the 2n plus 1. And the thing on the bottom is the same, 2n plus 1. It needs to be in parentheses factorial. That's a general term. And so now the closed form, n equals 0 to infinity, you just plug that nth term in there, x to the 2n plus 1 over 2n plus 1 factorial. Now, if we were to start at n equals 1 instead, you have negative 1 to the n plus 1 or minus 1, and then you have x to the 2n over 2n factorial. Now this converges for all real numbers. Negative infinity, positive infinity, interval of convergence. We never put brackets on infinity. Okay, cosine, same thing, but it's an even function, so you take all the even terms from e to the x, so 1 counts, x is 0, counts as even, and then it changes sign, minus x squared over 2 factorial, plus x to the fourth over 4 factorial, minus x to the sixth over 6 factorial, plus x to the eighth over 8 factorial, plus dot, 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 negative 1 to the n, x to the n equals 0, n equals 1, n equals 2, then it's just the 2n over 2n factorial. So in closed form, if we start at 0, it'd be negative 1 to the n, x to the 2n over 2n factorial in parentheses. If you were to start at 1, and I'm looking back and I may have made a mistake, n plus 1. So if you put n equals 1 here, n equals 2, n equals 3, n equals 4, what you'll notice is it looks like it's double this, minus 2, minus 2. So it's going to be 2 to the n minus 2, 2n minus 2 factorial. And it also converges for all real numbers, negative infinity to positive infinity. Now, in the last one, I think I may have messed up, so I'm going to double check this. N equals 1, n equals 2, n equals 3. So it looks like it's double n minus 1. So it should have been 2n minus 1, 2n minus 1 for sine. So I don't really try and memorize those. I know the pattern real quick, and then I could recreate the formula. Okay, next ones. You're going to have like 5 of these. Like the next 3, you're going to have like 5 of these on part 1 of your next test. And you need to write, I'm going to ask for a certain number of terms, and then also the closed form. But this one says of the given order. So kind of like some of these on part 2, I'm going to have just a certain number of terms, and then the closed form, and then on the next part 2, you'll have to do it like this too. Okay, so these ones, since they're Maclaurin series centered at 0, we can use the memorized versions that we're just doing. Now, I would write it down, the one you're going to use, real quick, just to have it in front of you. Even terms, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, right? And it keeps going. So ours, Taylor series, centered Maclaurin's a given order. So that's really a Taylor polynomial. So we usually write P for Taylor polynomial. It's 6th order x. And so what we do is we just take this and we plug 2x in for all the x's. So, I mean, we could do that. We could simplify it. 1 minus, that's going to be 4. So it's going to be 2x squared. This one's going to be 16 over 24. So that would be 2/3 x cubed. This one's going to be 64 over 127/20. So what do you get if you reduce this? Can we take a 8? I think so. This would be 8 times 90, right? And then 4 over 45. So 4 over 45, I think, would be the... Okay. So, anyways. All right. Next one's e the x. So I'm going to e the negative x. So I'm going to do e the x, which is 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So for us, this 5th order Taylor polynomial is going to be, we're going to plug in a negative x everywhere. So it's going to be 1 plus negative x plus negative x squared plus negative x cubed plus negative x to the 4th plus negative x to the 5th. If we were to simplify it, it'd be 1 minus x plus x squared over 2 factorial minus x cubed over 6 plus x to the 4th over 24 minus x to the 5th over 120. Okay, next one. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And then e to the 2x would be plugging a 2 in all these. So it'd be 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial. And then for us, the 4th order Taylor polynomial, we're going to multiply an x into all of this. And we're going to get x plus 2x squared plus 4x cubed over 2 plus 8x to the 4th over 6. Okay. All right. So, like I said, you're gonna have like 5 problems like that. I'll probably want they won't be order, but they'll rely on those memorized ones. And those will pop up on part 2 also, but those will be the second 5 questions. Part 1, part 2 will potentially have some questions like that, but also thrown in there will be other series not centered at 0. So these ones are the ones where you got to do the work. So natural log of x, centered at a equals 1, 4th order. So we need to go through and find all the derivatives. Fourth order, so we just need to go up to the fourth derivative. Don't do this when you don't have to, though, because it's a lot of work. Like if you tried to have done that on problem 15, it would have been a nightmare. I mean, it should work. It would have been horrible. Taking derivatives of this repeatedly, product rules and chain rules, and just, yeah. So we got those, and then we're going to plug the center into these. So natural log of 1 is 0, and that's going to be 1. And that's going to be negative 1. And that's going to be 2. And that's going to be negative 6. It's kind of interesting. It looks like it's alternating. It looks like these are actually factorial values. Not that we need those. So fourth order Taylor polynomial. It's going to be the first coefficient, 0, times x minus the center to the 0th power over 0 factorial, plus 1, x minus 1 to the first power over 1 factorial, plus negative 1, x minus 2, or x minus 1 squared over 2 factorial, plus 2, x minus 1 cubed over 3 factorial, plus negative 6, x minus 1 to the 4th power over 4 factorial. So that's a very unsimplified version. We could write a simplified version. That's 1, that's 1, that's 0. That term goes away. So it's going to be x minus 1 minus, we'll just leave these. I don't really want you to multiply those out. In fact, we'll probably start to just leave factorials a lot of times too. I mean, but definitely leave the polynomials with the powers. I don't want you to figure out what that would be. So, I mean, there's this, and then there is a version where we could simplify it a little more. I don't want you to foil those out though, for sure. I mean, we could do this. That's going to be 6. That's going to be 24. Oh, it's a cool pattern that comes out of this. Check that out. Like if you start simplifying these, just start getting these nice numbers. That worked out nice. Okay. Next one, centered at a equals negative 1, fifth order. This is your original function. So you got to crank these derivatives out. It's a little bit of work. Positive 2 over x cubed. Negative 6 over x to the 4th. 24 over x to the 5th. Negative 120 over x to the 6th. Then we need to plug the center into all of these. So you plug in negative 1 and you get negative 1. Here you're going to get negative 1 also. Here you're going to get negative 2. Here you're going to get negative 6. Here you're going to get negative 24. And those are factorials, by the way. 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. It's kind of interesting. And last one's negative 120. Okay, so it's not going to alternate, even though at first it kind of looks like it's alternating. So the fifth order, first term would be negative 1 times x minus x plus 1, because it's x minus negative 1, to the 0th power over 0 factorial, minus 1 over x plus 1 to the first over 1 factorial, minus 2 x plus 1 squared over 2 factorial, minus 6 x plus 1 cubed over 3 factorial, minus 24 x plus 1 to the fourth power over 4 factorial. And minus 120 x plus 1 to the fifth power over 5 factorial. So, I mean, that's one way we could write it. We could also simplify it really nicely. That's just going to be 1, right? Minus 1 minus x plus 1. Those cancel. Minus x plus 2, x plus 1 squared. Those cancel. I mean, it worked out those, because those numbers on top are just the same factorials. I definitely don't want you to FOIL out the binomials, though. Okay, last one. So that's we're looking for order 4. So this is your original function. First derivative, 3x squared minus 2. Second derivative, 6x. Third derivative, 6. Fourth derivative, 0. And then they just go away. So we want fourth order, but the fourth order term, the fourth degree term, isn't going to be there. That's fine. It's still fourth order. We put it in there. It just has 0 coefficient. So then we're going to plug 2 into these. And so that's going to be 8 minus 4 is 0. And then that's going to be 12 minus 2 is 10. And that's going to be 12. And that's going to be 6. And that's going to be 0. So the fourth order Taylor polynomial is going to be 0 times x minus 2 to the 0 power over 0 factorial. You don't have to write that. That's 1. That's a 1. I just like because it's the same pattern. Plus 10 x minus 2 to the first power over 1 factorial. Plus 12 x minus 2 squared over 2 factorial. Plus 6 x minus 2 third power over 3 factorial. Plus 0 x minus 2 to the fourth power over 4 factorial. So this is a very rough version, but we could simplify it quite a bit. That first term just drops out. So we get 10 x minus 2 plus 6 x minus 2 squared plus x minus 2 cubed. Let me just double make sure. Okay, 8. Oh, shoot, I messed this first one. 8 minus 4 plus 4 would be 8. So there is an 8 there. Ugh. A little mistake there. Anyways, there you go. So we're going to have some of these on part 2. A bunch of these where some are centered at 0, so you can use a shortcut. Some aren't, like this. You got to just do it the long way. So there you go. This is a good review assignment. Didn't have error on it. Didn't have any of that kind of stuff with Lagrange error bound, which will also be in your test. So that'll be on the next assignment, the pretest.